Welcome to the Java Collections Framework Mastery and Interview Guide, brought to you by Interview Tech Bytes. Let's begin by comparing standard arrays to the collections framework. Standard arrays are fixed in size, meaning once they are instantiated, their size cannot be dynamically changed. They have the ability to hold both primitive data types, like integers and doubles, as well as objects. While arrays are a core feature in Java that offer high performance, they lack built-in utility methods for manipulation, sorting, or searching. On the other hand, the collections framework is dynamic in size, growing and shrinking seamlessly at runtime. Collections can only hold objects, meaning primitives are autoboxed into wrapper classes. The framework provides a massive architectural system of interfaces and classes equipped with ready-to-use algorithms for complex data manipulation. It's important to understand the difference between legacy and modern collections. Java 1.0 introduced legacy classes like vector, hashtable, stack, and dictionary, which are synchronized by default. Because these classes are synchronized, every operation acquires a lock, which results in a performance hit, making them significantly slower in single-threaded environments. To modernize this, Java 1.2 and later versions introduced ArrayList and HashMap to the framework, which are strictly unsynchronized by default to achieve maximum speed. As a quick interview tip, if you are asked to compare vector and ArrayList, the critical differentiator is their synchronization and performance. Now let's look at the core hierarchy. List. A list is an ordered collection, or sequence, that carefully maintains the insertion order and explicitly permits duplicate elements. Accessing elements by their index is a primary feature of a list. Set. A set is a collection that contains no duplicate elements, modeling the mathematical set abstraction. Generally, a set does not guarantee any specific iteration order. Queue. A queue is a collection designed for holding elements prior to processing. It typically orders its elements in a first in, first out, or FIFO manner, which is essential for task scheduling. Diving deeper into the list interface, we have ArrayList and linked list. An ArrayList is backed by a dynamically resizing array. It excels at fast data retrieval and random access due to its index-based searching. However, its performance degrades significantly during insertions or deletions in the middle of the list, because elements must be shifted in memory. A linked list is backed by a doubly linked list data structure, where elements, or nodes, hold pointers to their previous and next siblings. This makes it excellent for frequent insertions and deletions since you only need to update pointers. However, it is extremely poor for random access, requiring O(n) traversal. Moving on to the set interface, let's compare hashset and treeset. Under the hood, a hashset is actually backed by a hashmap instance. It makes no guarantees as to the iteration order of the set. Assuming a good hash function, it provides constant time performance for basic operations like add, remove, contains, and size. It also allows exactly one null element. A treeset, conversely, is backed by a treemap, which is a red-black tree. Its elements are ordered using their natural ordering, or by a comparator provided at the time the set is created. Its operations take log n time. Note that null elements are explicitly forbidden in a treeset and will throw a null pointer exception. Here is a frequent interview curveball. Why isn't a map a collection? The Java util map interface is undeniably part of the Java Collections framework, yet it intentionally does not extend the Java util collection interface. The reasoning is structural. A collection operates on single elements using the add method, whereas a map requires key-value pairs using the put method. Forcing map to implement collection would break interface segregation and create illogical, unsupported method requirements. Let's clarify the difference between the collection interface and the collections utility class. The Java util collection interface is the root of the hierarchy implemented by list, set, and queue. It defines the standard behavior for these collections. In contrast, Java util collections with an S is a utility class consisting exclusively of static methods. It acts as a toolbox for manipulating or returning collections. It houses algorithms like collections, sort collections, binary search, and methods used to create synchronized wrappers. Another subtle interview question is, why don't the list or set interfaces extend clonable and serializable? The answer comes down to architectural freedom. Forcing the root interfaces to be serializable places an unreasonable burden on custom, specialized implementations. Practically speaking, however, 100% of standard concrete implementations like ArrayList, HashSet, and HashMap implement both clonable and serializable out of the box. Performance is critical, so let's review the big O time complexity for common operations. For an ArrayList, accessing data is O(1), inserting is amortized O(1), deleting is O(n), and searching is O(n). For a linked list, accessing data is O(n), inserting is O(1), deleting is O(1), and searching is O(n). For a hash set, accessing via an index is not applicable. Inserting, deleting, and searching all take O(1) time. For a tree set, accessing via an index is also not applicable. Inserting, deleting, and searching all take O(log(n) time. When iterating over collections, you must understand fail-fast versus fail-safe iterators. Fail-fast iterators operate directly on the collection itself. If the collection is structurally modified by any means other than the iterator's own remove method while iteration is in progress, it immediately throws a concurrent modification exception. These are used in ArrayList and HashMap. Fail-safe iterators operate on a cloned copy of the collection, not the original. Structural modifications on the original collection are ignored by the iterator, which safely prevents exceptions. These are found in concurrent packages like copy on write ArrayList and concurrent HashMap. The golden rule for interviews is this: never use a standard fail-fast iterator to safely delete elements concurrently in a multi-threaded application. Always utilize concurrent collections for thread safety. How do you choose the right collection? Follow this simple decision tree. If you require key-value data mapping distinct keys to values, bypass collection entirely and use map. Choose HashMap for speed or tree map if your keys must remain sorted. If your data must be unique and duplicates are strictly forbidden, use set. Choose HashSet for constant time performance, or TreeSet to enforce natural or custom ordering. If you need precise insertion order and duplicates are allowed, use list. Choose ArrayList for fast reads, or linked list for queue-like rapid manipulation. Sorting often requires choosing between comparable and comparator. The Java, Lang, comparable interface provides a single, default natural sorting sequence. It requires modifying the class whose instances are to be sorted by implementing the compare-to method. This is useful for fundamental domain objects, like sorting employees universally by their ID. The Java, util, comparator interface allows the creation of multiple distinct sorting sequences. It operates outside the class being sorted by implementing the compare method. This is perfect for custom sorts without modifying the original source code, such as sorting employees by name, and then by age. To summarize, here are 3 key takeaways. First, performance first. Always know the big O time complexity. Choosing the wrong collection structure is the #1 reason for production bottlenecks. Second, understand the hierarchy. Grasp the difference between root interfaces like list and set, and their concrete classes. Code to interfaces whenever possible. Third, ace the edge cases. Interviewers love the map exception, fail fast logic, and